Let's do an example now. Let's put three charges on a triangle and let's draw the electric field lines and the equipotential lines. A lot of things to remember here. We remember that electric field lines go out of positive charges. We know that the number of electric field lines is proportional to the size of the charge. All of these charges have the same size, so they'll all have the same number of lines. We know that electric field lines can't cross because that would mean they had two directions at the same time, and that's not physically possible. With our equipotential lines, every equipotential line has the same potential. They're all evenly spaced in potential, and all of those equipotential lines are perpendicular to the electric field lines. Let's start by getting the idea with a PhET simulation. By all means, do this along with me, and then let's draw it all in by hand. So here's a screen cap of a video I did doing that exact same thing. We'll start by putting in a positive charge. Immediately the electric field lines come up. Where the lines are bright, the field is strong. Where the lines are dim, the field is weak. When I put the three charges in, it looks like the field is 0 at the middle and it's strongest in the middle. The red indicates the strength of the potential, and now I move my sensor around till I find the potential. I'll draw my first line at about 25 volts. Looks like one of those fidget spinners. Draw my next line out at around 20 volts, so I'm going to space my equipotential lines by about 5 volts. Then as I move in, I'll draw my next line at 30 volts. It's kind of a circle around that lower right-hand charge. Draw one more at around 35. It's hard to be perfect on those. Then I'll draw lines around the other two charges. So we see we have circles in close to the charges and kind of a blob around the circles outside. In close to the charges, the electric field is strong, so the equipotential lines are close. Further away from the charges, the field is weaker and the equipotential lines are more spread out. So these simulations are super for when you're trying to draw these field lines. They can really help you visualize it. You should understand the theory to be able to draw these without a simulation, but this is a great tool just to make sure you're on the right track. Okay, now let's go through and let's make an actual sketch of what we just learned. So we've got three charges, they're positive. I'll draw the electric field lines in red. I know that the electric field lines go away from the charges. My charges all have equal magnitudes, so they should all have the same number of electric field lines coming out. So they're all coming away from each other. I have 3 on each one now. I'd like to get a little bit more of that interaction between the charges. So I've got 1, 2, 3, 4, 1, 2, 3. I've got 4 on every line. I could squeeze in a bit more, but it's looking a bit full now, so I think I'll stop. Next, so those are my electric field lines. I'll label those with an E. Next, I'll put in my equipotential lines. Remember, those are circles that go around my charge. They're close where the field is strong, and they're more spread out where the field is weak. And we've got a symmetry to this problem, so there's going to be a symmetry in the electric field lines. Okay, and then we've got our fidget spinner on the outside. Oops, I kind of goofed there. I don't like how this turned out, so I'll just, oh my, I erased some of my electric field lines when I meant to be erasing the potential lines. Get those back in there. Okay, that's kind of recapped pretty well. So these are my equipotential lines. Equipotential lines. Okay, so there's a sketch of what we would have. We can do some work with this diagram. So I'm going to go back to the PhET simulation sketch and we'll look at what could we figure out from these diagrams. So one thing about these diagrams is that you know what the potentials are. This is a picture here I took from the simulation. The only thing I did was I turned on the values, so it shows what the potentials are at the different places. If we remember that our electric field is the change in potential over the change in distance, then if we know the change in potential between any 2 points and the distance between any 2 points, we could actually find the electric field at the midpoint of those 2 points. So let's pick 2 places on our diagram. Let's see, I'll pick down here on the bottom right. Now I've identified 2 spots on my graph. I can find my change in potential because the line on the left that I drew a dot on, everywhere on that line, the potential is 24.8 volts. So one of my potentials, V1, is 24.8 volts. The other potential, where I drew the other dot, that one has a potential of 30 volts. V2 is 30 volts. The distance between those 2 spots, I can measure those. I have a scale here on my diagram. So 1, 2, that looks like about 2.5 lines times 100 centimeters for every 10 lines. So that's about 25 centimeters. Okay, so I'm just using the scale here and counting the number of lines and finding that. So my delta S is about 25 centimeters. If you were doing this for an assignment or a test, you'd probably try and be really careful about that measurement just to get as accurate as you can, or if you were doing some research. So now I'm all set to find my electric field at the midpoint between those 2 spots. So E equals. So my electric field strength at that point is going to be minus delta V over delta S minus 30 volts, take away 24.8 volts, divided by 25 centimeters, which is 0.25 meters. Just grab the calculator. 30 minus 24.8, divide that by 0.25, and we get 20.8 volts per meter. So that gives us the strength of the electric field. The direction of the electric field is going to be straight towards the left because it comes out of the positive. And at that point, it's probably starting to turn a little bit. We know that the electric field is perpendicular to those lines. It's kind of hard to get exact directions from these potential diagrams. Okay, it looks something like this. So mostly what we use these diagrams for is for getting the strength of the field. So the magnitude of the field at that point is 20.8 volts per meter or newtons per coulomb. Those are equivalent units. In this example, we're going to use the expression for the electric field between the plates of a capacitor. And as a reminder, that's E equals sigma, the charge density, divided by epsilon naught. And the direction is from positive to negative. We're going to use that with delta V equals minus E dot ds, the integral of all that. I'm going to use that to find an expression for the electric potential between the plates. And then we're also going to draw the equipotential lines. Before we get started in the math, we can have a look at a couple of pictures if you wish. I nabbed this picture from a FET potential. I put in a line of positive charge, I put in a line of negative, and I turned on the electric field. You can see it goes pretty much straight across, a little bit of bending at the end because it's not perfect, it's just kind of close. Okay, there's a picture of the electric fields. In this picture, I click the button to turn on the potential. This bright red here is the positive potential, this blue is the negative, and right here is 0. One thing we might remember is that the positive plate will be at a higher potential than the lower plate because electric field points from high potential towards low potential. Here I drew some equipotential lines. I just moved my sensor around until I hit some values I liked. Straight down the middle is 0. To the left of that is our positive potentials. To the right of that is our negative potentials. In the middle, they're pretty much straight up and down. Towards the top, they're starting to curve. That's because my capacitor here is not perfect. It's just a simulation. You see that they're pretty much evenly spaced in distance, and that's because our electric field is constant. Let's get started now finding the expression for the electric potential between the plates of the capacitor. Let's get some things down so we're sure we know what we're doing. First is our expression for electric field. It's the charge density, so the net charge on a plate divided by the area of the plate, divided by our constant epsilon naught. and the direction is from positive to negative. Okay, we also need a coordinate system. Typically, we call our coordinate system S. We put S equals 0 at the negative plate, and typically we say S equals D at the positive plate. So this axis is the S axis. All right, so I think we can write down our expression for potential now. The change in electric potential is minus the integral of E over the path. Okay, let's think about what the path is going to be. We're going to start at the negative plate and come to some generic point here. Okay, and this generic point is just going to have some value of S. Let's call this path S primed, and a little bit of this path is going to be ds primed. Okay, I don't want to get my s's confused, so the s-axis is this one, so I'm going to call this path S primed, and a little bit of this is ds primed. So in my integral, it's the electric field over the path ds primed. This is a scalar product, so that's the magnitude of the electric field times the magnitude of the path element times the cosine of the angle between the path and the field. My electric field points to the right, my path points to the left. This angle is 180 degrees. Okay, so they're anti-parallel. That means, so cosine of 180 degrees is -1, so my delta V then is the integral of E times ds, the magnitude of the field times the path element. The limits of our integral, we're starting at the negative plate, that's s equals 0, and we're stopping at some general point between the plates, so some value of s. All right, we can take our expression for electric field and fill it in right here. So delta V is equal to the integral from 0 to s of sigma divided by epsilon naught, integrated by ds primed. Constants come out front, and that's sigma and epsilon naught. Both of those are constant. So we've got the integral of ds primed over our limits. The integral of ds primed is just s primed. That has to be evaluated at our limits of s and 0. So that's going to be equal to sigma over epsilon naught times s minus 0. So for our final result, we've got delta V, and that's going to be our final potential. Subtract our initial potential, the definition of a potential. It's equal to sigma times s over epsilon naught minus 0. Okay, let's introduce the idea of a reference point again. So for our reference point, we can take VI equal to 0 at s equals 0. Okay, so this spot we're going to say has 0 potential. So this whole term is 0. And then just to simplify, instead of writing VF, I'm just going to write that as V. So now my final result is that the potential at some point between the plates is V equals sigma times S divided by epsilon naught, where S is your distance from the negative plate. Okay, so that takes care of our equation for the potential. If you wanted the total potential difference between the plates, then your S would be equal to D. Why don't we put that in brackets? So if you wanted the total potential, you just put in V, or you put in S equals D. Okay, that takes care of finding the potential between the plates and the total potential. Next, let's draw the equipotential lines. The last bit we're asked to do is draw our equipotential lines. Remember, an equipotential line is any line along which the potential is constant. We know it's going to be perpendicular to the electric field lines, and we know the electric field lines point towards lower potential. So in our expression for V, we see V is equal to sigma over epsilon naught times the distance from the negative plate. For V to be constant, S is going to have to be constant. Okay, V is proportional to S. So if S equals 0, the potential is also 0. And that will give us an equipotential line that comes right down through right here. V equals 0. Our next equipotential line would happen when S gets a little bigger, and then a little bigger, and then a little bigger. And our last equipotential line would happen when we hit the positive plate. So if S equals D, we see that V is equal to sigma times D over epsilon naught. So indeed, our potential here, V equals sigma D over epsilon naught. This value is big and positive. This value is 0, so the electric field lines are pointing towards lower potential. What else? The equipotential lines are perpendicular to the electric field lines. So many E words here to say. So we see that the lines are parallel to the plates. We also see that the lines are evenly spaced in distance and evenly spaced in potential.